But overall, who did the homework? Yes, did it work out? Kind of, sort of. All right, I'll do it now. But just to give you a little bit of an idea of a couple of things. One, what were the changes that were needed in the code, which were actually fairly minor, I would say. So I will try to show that. And then two, I have it here already. Okay, yes, I have that. Okay, so I'll do that. To give you a bit of an idea of what are these different strong forms and what do they represent, so that it's not an arbitrary equation. So problem one, the strong form was the K DDR R DTDR plus S times R equals 0. This is the standard heat transfer problem, but it's on, so this is heat transfer, but in cylindrical coordinates, or the polar coordinates. So it almost looks exactly like the standard heat transfer. The only difference is the dependence on R. And this is because of the axisymmetric problem. I shouldn't say linear, but just the 1D heat transfer. In X. So this is still a 1D equation, but it represents basically, if you had a circle, it represents a slice of that circle, where R is the radial coordinate, but it doesn't have to be aligned with the X axis. So I guess I'll do it in some random orientation. And then the problem is 1D, because even though in polar coordinates, even though this is a 2D object, this is a disk, the other coordinate, which is theta, does not have an effect. There's no change with respect to theta. So axisymmetric problem means independent of theta. So technically, we are solving a 2D problem, but because it doesn't change with respect to theta, then you can solve it along just the radial direction. But then to plot it, you could plot the solution of that homework problem one. You could plot it along R. So you could, for your solution, you could do, so for solution, this means that you could plot along R, whatever the temperature looks like, right? Or you could try to plot it like a contour. And then it would just have concentric, where the same value of R will be used for every, same value of the temperature will be used for any given R. So it is really a 2D problem, but it's the heat transfer problem. You can see that it's basically diffusion in the direction of the gradient of the temperature, and there's some source term. So this basically is the diffusion part, and then this is a source term. So there's some heat source that depends on R. And there were two types of boundary condition. There was T at R equals 0, and there was dTdr at I equals 0 equals 0. I think those were the two boundary conditions. This one always makes sense for this type of problem because there's nothing that can flow at the center. So that one is basically what is the flux at this center of the circle. And the flux at the center of the circle, if the problem is independent of theta, then there cannot be any flux going into that point. Because if there's some flux, then it would break the symmetry of the problem. So if we claim that the problem is axisymmetric, then there's just no way to have a flux. So that's a very reasonable assumption that comes from the axisymmetric. And then the other one is just, that one is arbitrary. It's just we decide that there is some reservoir, typically this type of essential boundary conditions. So essential boundary condition are related, in the case of the heat transfer problem, there's some reservoir, right? So some heat reservoir at constant temperature. That's basically what the essential boundary conditions are. So in this case, basically we are assuming that outside of this disk, there is, I don't know, a lake or something that basically keeps a very big object that keeps the temperature at 0. That's basically the physical meaning of that other boundary condition. And the source term, meaning we are putting some heat into so this SR, we're just pumping some heat into the plate. I don't know, there's some heating system underneath the plate. And in this case, it depends on R. It's just linear with respect to R. So the farther away you go in the plate, the more heat source you have. That's the physical meaning. What to expect with, and this is more related to also to the second problem, but in general, what does diffusion do? So what, if you had no source term, do you know what the diffusion solution would look like? So if you have, for example, dt the x squared equals 0 with some essential boundary conditions. Do you know what the solution is? That you might have done in your classes, your like PDE class or the E class. Any guess as to what the solution for this type of equation would be like with some two essential boundary conditions? Any wild guess? Yes. And what does so what thing, if you take, this could be a polynomial indeed. And typically you have some exponential decay. So when you have some diffusion and you have, it's a smooth version of, you always get smooth solutions. You get some exponential decay of the trivial equation. And then, yes, you have some, I guess, particular solution. But you should think sort of decaying. So if you fix the temperature at 2 points, then it will decay with some characteristic length scale. And in this case, and it's always smooth, irrespective of what the boundary conditions are, which could be discontinuous. So in this case, we have no flux on the left-hand side, and we have fixed temperature at 0 at radius equals R, and we have some heat source over the domain. So because this is fixed at R equals R, it will definitely end up at 0. And then we have some heat source, so that will definitely accumulate. And you have no flux on the left. So this is why this one will basically raise the temperature. I don't know exactly how the profile looks, but it should start from 0 and then it should increase to the left. I don't actually know if it increases, probably increases like that because the heat source is greater at the end. So it probably has this type of concave shape to it. So basically you are kind of inflating, imagine that you are inflating. So you are pumping heat, but you are pinning it at the end. So it will rise and there's no constraint on the left. So it will just, it's basically if you are pumping water into this, it will kind of rise like a balloon. Imagine a vast balloon. And then your S is sort of the amount of water that you're pumping in. So it looks something like that. Now, in terms of how do you solve this temperature profile? You had to go from the strong form to the weak form. I'll just skip directly to the weak form. So you have K R dW dr dt dr where omega, and then minus, you either put the minus here or in the other one, it doesn't matter. WSR equals 0. So this is what your weak form should look like. There's no, I mean, the natural boundary condition is 0. So when you do the integration by parts, actually the integral over the boundary disappears. So this is what this looks like for all W. So the first term should give you the stiffness matrix. And this term should give you the force vector. For the stiffness matrix, the difference between this and the problems that we have done in the past is just this R, which changes a little bit the stiffness matrix, because the stiffness matrix will look something like this. So if you plug in, remember that to go from here to the stiffness matrix, you plug in the fact that you can express the temperature and the gradients as the sum of the shape functions times the nodal values. So if you use that and you plug into the weak form, then you're gonna end up with, and you take out, you do a little bit of algebra, so you take out the sums. K, R, D, N, I, dr, dtj, dr, tj. And this is your stiffness. So if you actually expand it, it will look like this. So this one will be the integral of kr dn1, just the 4 combinations, dn1, dn1, integral of kr dn1, dn2, integral of kr dn2, dn1, integral of kr dn2, dn2. And here, because we are doing it over the element, we're going to integrate from the beginning of the element to the end of the element. These derivatives, dn1 dr, that one is just -1 over the length of the element. dn1 dni is also -1 over the length of the element. So if you integrate this out, and I don't care how you did it, if you did it with Gauss quadrature, if you do it analytically, I was fine either way. Actually, you can take out, so this ends up being R2e squared minus R1e squared over R2e minus R1e squared, k, and then 1 minus 1 minus 1, 1. So it looks a little bit different from the stiffness matrix that we have been using, and this is just because of that extra R term that we had. The force vector is the same. I'm not going to do the force vector because the force vector is same as PL3. In PL3, you have W, and instead of SR, you have BX or CX, but it's the same. It's just W times a constant times X. So in this case, W times a constant times R, but everything is in as a function of R. Same as PL, just C goes to S, X goes to R from PL3, but the rest was the same. So actually you could just reuse my code for that. So really, as I was saying, the only thing that you have to change is this. And yeah, that's about it. I'll do it in 1 sec, but I'll just go a little bit over problem 2 as well. I feel like I did some of this on Monday already. My memory is terrible. But for problem 2, you have V. I just don't know if I did it in class or if I did it in office hours. And then I don't know if there was a K here. But something like this was the problem 2. And this one is the advection diffusion equation. Where this is the diffusion part. And this is the advection part. And like I said, diffusion always tries to make it smooth. So the diffusion would have, in this case, the problem had 2 essential boundary conditions. So the theta at 0 was 0, the theta at 1 was 1. So here x equals 1, x equals 0, theta equals 0, theta equals 1. So if you just had diffusion, then you would have some basically exponential decay here. Some nice little decay. And then the advection term, you should think of that as associated with some flow. So if you have you done in fluids or in heat transfer, you can transfer heat because of convection, advection, convection, or diffusion. So diffusion is just nearby contact of particles. If you have a few particles that are in contact with each other, they will agitate nearby particles, and that's how you propagate heat. But you could also have a flow. So if there's some underlying flow, that will carry some of the heat. So that term V d theta dx is basically heat transfer due to a flow. That V is actually a velocity. So this is heat transfer, this term right here. Flow carrying heat for your transport problem. And so what that does is that it can squish in depending on how the flux looks like. It can squeeze in this other profile. So if you have, so you will squeeze it into a shorter range. depending on how strong your flux is. That's why the solution looks like that. And that's sort of the physical meaning behind this one. I have to say the reason why I pointed you towards this is because this is, for example, the type of problem where if you just do the standard FE stuff that we have been doing, it will lead to unstable. So the FE formulation from class becomes unstable for large convection or advection. And that is illustrated in the book. So if that V term is high, if the velocity is high, then what happens is that you end up having oscillatory solutions. So that would be something, and it's illustrated in the book, but that would be something like this. When V is high, say V greater than, I don't know what the dimensional unit is for. I think it has to be high with respect to the K. Then you get this type of oscillations. So in that case, actually you need to do special things, which we are not covering in class. So for convection dominated problems, Abacus does not have, I think, I have not used the flow solver in Abacus, but for example, in COMSOL, for example, and probably in ANSYS, you have to pick stabilizing methods. So in the options, you have to look for it. You have to pick stabilizing parameters, stabilizing formulation and parameters. We're not going to cover that in class, but that's something that you have to be aware of because of the types of problems that we're not doing in this class. But if you ever have to solve convection dominated problems, you have to be careful with stabilizing your formulation, or you're gonna get a lot of oscillations that are unreal. It's not really what the solution should look like. Yeah.
That was my question. They were real.
No, the correct solution is probably more like a very sharp increase. So it kind of gets pushed and then goes up sort of very fast. So yeah, they're not real. And the reason why you have to be careful with this is because you can do it too much. So the way that these stabilizing formulations work, they try to estimate a couple of things. For example, the direction of the flow, and then weight more information ahead of the flow with respect to in the wake of the flow. They can add a little bit of diffusion to try to regularize the formulation in special ways. And so you have to be careful, because if you overdo it, then you're adding too much diffusion, then it's not the correct problem that you're solving. But for the problem in the homework, it was with a small v, such that it was still stable with the FE formulation, so you get no oscillations. Questions? All right, so I'll just show, since I have your attention. I was doing it on the office hours, but I'll just show you the solution, at least of problem 2. And let's see. Make sure I mute myself. Just mute. All right, so let me stop sharing here. And then let me share here. So this was the solution of problem 2. This was the solution of problem 2. I don't think I have solution of problem 1, but the standard thing. By the way, this is based on the PL3. So I took PL3, I duplicated the notebook. So this is the exact same as the beginning of problem PL3. This is, I was creating the mesh. So here 20 elements. The one thing that you needed to be careful with creating the mesh was to ideally put the nodes with essential boundary conditions first. So the node at x equals 0 and the node at x equals 10 had essential boundary conditions. So I just made sure that my first 2 nodes were those. So 0, 10, and then all the other nodes are ignored there. So 0.5, 1, 1.5, 2, 2.5, and so on, up until 9.5. So this is my node x vector. Again, I think it was convenient to, if you wanted to do matrix partitioning, convenient to just put the nodes with the essential boundary conditions first. So this was my node x. Then given this, what are my elements? So my first element, which has coordinates 0 and 0.5, is node 0, but with node 2. Then from then on, they were easy. So 2 and 3, 3 and 4, and so on, 4 and 5, and so on, up until the last one. So this is node 19, and this is node 20. So the element 19, 20, but then the last element is node 20, and then node 1. So that's why my last element is 21, 20, 1. Again, you just needed to be careful with how you define your elements, but hopefully if you can do it by hand. I would suggest to draw it out by hand and then just type it in. I didn't do that in the office hours. I was trying to just do it with some piece of code. But if you just draw your mesh and name your nodes and name your elements, all you have to do is transcribe that to the node X array and to the element array. Then again, this I was using from the code, and I basically deleted, for this one, there was no force vector. So I deleted the force vector, and the only thing that I changed was the KE. This is the KE from the book. So in the book, I didn't derive it for now, but in the book, it was already derived. I forgot the page, but the KE for the advection problem was already defined. I know Andrew was showing it to me on the book, so it was there. You could just use it. So I just used that, and that's it. The rest of the code is the exact same, and I deleted all the force vectors because for this problem there was no force vector. This is what the stiffness matrix would look like. Then the partitioning, in this case, there were 2 essential boundary conditions. So the first 2 nodes had essential boundary conditions. So I just changed that here. I just said n EBC equal 2. That's it. Because then it would partition with, the 2 by 2 with essential boundary condition. And then the solution, this again was the same. So KF inverse times FF minus KF times UE. And FF is 0. KF is whatever was from the matrix partitioning. And UE is basically the value of the essential boundary conditions. So in this case, the essential boundary conditions were 0 and 1. So this was the other change that you needed to assign the correct boundary conditions. And then I just solved exactly what I wrote right here. So UF equals KF inverse FF, which was 0, minus KF UE, which is what I solved here. And if you solve that, then it gives you the solution. And then you just plot it again, just reuse the code and plot it. And this is the solution. So this is what it should have looked like. Questions? Again, I would say the main things were small changes, but I guess very important changes. One, to be careful with your mesh. Make sure that your nodes with essential boundary conditions are first. I think that was one thing to be careful with. And to have a consistent mesh. Then to change the stiffness matrix, and you could follow the book one for the element. And then I would say the next important thing was to assign the correct essential boundary condition, which was 0, 1, and then use that in the solution of this UF. Did it work? It worked. All right, I'm not gonna do the other problem because I do want to do a little bit of the FE in 2D. But for the other problem, again, the main difference was just that KE, was just changing the KE. The other problem had a force vector. So that one you had to keep. But you have to be careful again with how you define your mesh, just to make sure that the first node was the one with the essential boundary condition. Then to change the KE. And that's pretty much it. So we'll post the solution. But yeah, if you have any questions, I think that now is the moment. All right, otherwise we'll try to do at least a little bit of the problem 2. Of at least a little bit of the finite elements in 2D. So going back to 2D, what we're after is basically the exact same thing that we did for 1D. So we had a strong form, and we converted that to the weak form. And the process is the same. You multiply by a weight function. You do integration by parts, but in 2D, integration by parts is called Green's formula, but it's the same idea. And then you get a weak form that looks very similar to before. I have it in the next slide. That was one, and that's what we did last week. And then what we did on Monday was we introduced at least the triangular elements. And then when you plug both of these together, we will get a system of equations. I think I'll do that after spring break. I don't know if I have time today, but strong form. This was the strong form of the heat transfer problem. Divergence of the flux minus a source term equals 0. The flux by Fourier's law is minus the gradient of the temperature with either natural boundary conditions, so that's known fluxes, or essential boundary conditions, that's known temperatures at the boundary. So from doing the weak form, you end up with a similar statement to before. So find temperature, which now is a function of x and y, such that the gradient of the W times the gradient of the temperature. This looks a little bit different than in 1D. We had dt dx and dw dx, but that's because it was a 1D problem. Here we have gradient. So gradient of W times gradient of T. And then this D is just the conductivity. So if that one is the identity, then it's just gradient of W times gradient of temperature. It's a matrix because it could be anisotropic. So actually for your previous lab, you solved this problem and you actually used a D that was not a multiple of the identity. You used different conductivity in different direction. So that one equals, this is gonna be a force vector. So obviously this is gonna lead to some stiffness matrix. This is gonna lead to some force vector because of boundary fluxes. Note that this is an integral over the boundary. And this is gonna lead to a force vector out of the source term. Right, so the W times the S will give us a force vector. The W times the Q will give us another force vector, but this one is over the boundary. This one is over the domain. This is boundary flux. And this is basically flux from source. I mean, it's not a flux, but it's a source. So in order to discretize that weak form, we need to introduce shape functions. There's obviously the shape functions we can define directly in terms of x, y, but these typically only doable for triangular elements. So for triangular elements, we actually have, some functions of x, y that we can use, but generally not very good for integration. So if you want to do integration, then what I did on Monday was this map, where I said, I'm gonna map every triangle to this parent domain triangle, which is always this one right here, which has corners at 1, 0 and 0, 1 and 0, 0. The shape functions in this triangle are super simple. It's just the first shape function is just psi1, the second shape function is just psi2, and the third shape function is 1 minus psi1 minus psi2. And then we have the isoparametric map. So how do we get x in terms of psi? And we also have the Jacobian of the map, which is just the gradient of this map. So this is just, the Jacobian is just the gradient of x with respect to psi. And it's a 2x2 matrix. And maybe I'll add one more thing. So given the map and the Jacobian, if you also have nodal values for theta, so for the same element, you not only have the x1, x2, and x3, but you also have nodal values, theta 1, theta 2, and theta 3. Then you can use the same shape functions to interpolate theta. So theta as a function of psi is going to be the sum of the shape functions in terms of psi times the nodal values. And then if you recall this, we will want the gradient of theta with respect to x coordinates. That one we cannot compute directly because we don't have theta as a function of x, we only have theta as a function of psi, but we also have the Jacobian of the map. So actually, if you want, so if you use chain rule, I did that last time. So the inverse of the Jacobian times the gradient of theta with respect to psi, where the gradient with respect to psi is the sum of the gradient of the shape functions with respect to psi times theta I. So the things that you can compute is you can compute this, you can compute this, you can take the inverse, and then you can compute this. And doing those three, you can get the gradient with respect to x. Questions? So for integrals, I don't think I have this one in have the quadrilateral, but I'll just say for the triangle, there are tables. So it's going to be the same as before. So you have the integral over some triangle of some function. Let's say that is a function of x. dA. Well, I'll put dx dy. So let's say I have some integral that has to be done in the xy space. I want to integrate over xy, some function of x. But I don't want to do the integral in xy. I want to do the integral in another domain. So the same idea as before, I'm gonna do the integral in my parent domain. So I'll do integral in parent domain. And this is just a change of variables. So it's the same idea from what I said before. So we are gonna use the map, the fact that I can express x as a function of psi. And then here I need the determinant of the Jacobian. Because now, before I just used the Jacobian, but the Jacobian was a number, now it's a matrix. So I just need the determinant of that. This I1, this I2. So from the first integral over some xy space to the integral over psi1, psi2, I just do a change of variables, and I need that determinant of the Jacobian. And then to approximate that integral is gonna be a sum of the weight of the integration point times the function of x of psi at that integration point times the determinant of the Jacobian at that integration point. Move this a little bit to the left. And that's it. So it's the exact same idea as the Gauss quadrature, and these are from tables. So WIP, PSI-IP from table. I have it in the slides from Monday, actually. This is not called Gauss quadrature because it's integral over a triangle and not integral between -1 and 1, which is what the Gauss quadrature is. But the idea is the same. Questions? All right, so I'll just sketch out how it works for quadrilaterals. For quadrilaterals, it's the same thing. There's some quadrilateral, we have coordinates for the quadrilateral, but we don't want to use shape functions over the quadrilateral. So what we do is we define a quadrilateral that we like between -1 and 1. So this is our parent quadrilateral. And we're gonna use the exact same concept. So what do? Is we define shape functions in terms of psi and eta. There's 4 nodes, so there's gonna be 4 shape functions. And this basically is the formula for all 4. All you have to do is plug in, these different combinations, and then you get your 4 shape functions. So these are the shape functions in terms of, 4 shape functions in terms of psi and eta. So again, given that you have your shape functions in terms of psi eta, then you can use the isoparametric map. It's the exact same as before. So the x as a function of psi eta is just going to be the sum of the shape functions, which are functions of psi eta times the x coordinates. Then the y is just the sum of the shape functions times the y coordinates. You can get the Jacobian. It's just the sum of the derivatives of the shape functions times the x and y coordinates. Again, you can invert the Jacobian. Then if you have, it's the exact same idea. If you have some theta, so you have theta values, for example, temperature, and you want to interpolate, exact same thing, sum of the shape functions, which are functions of psi eta times the nodal values. If you want to get the gradient first calculate the gradient with respect to psi eta, and that's just the sum of the derivatives of the shape functions with respect to psi eta times the nodal values. And then if you want to get the gradient with respect to x, then you need to multiply by the inverse of the Jacobian. So it is the exact same thing as for the triangle. It's just that here you have 4 shape functions and they are different. For the triangle, there's 3 shape functions in terms of psi eta. Here there are 4, and they are given by this, by here. So if you just follow this definition, then you get these 4 shape functions. But the other expressions look the same. So x, y is just sum of shape functions times x, y coordinates of the nodes. The Jacobian looks the same. Again, the interpolation of any function is just the sum of the shape functions times the nodal values. You can directly take gradients with respect to psi, and then if you want gradients with respect to x, just multiply by the inverse of the Jacobian. So same idea. And I have 1 minute left. So the last thing that I'll do, and then we'll continue that on Monday after spring break, is integrals. So if I have an integral, again, of x dx dy over some quadrilateral, that is going to be the same as integrating over my nice parent quadrilateral of f of x of psi. So I need to get my function in terms of psi times the determinant of the Jacobian, d psi d eta. And again, how I'm gonna compute this, this is not an equal sign. I'm gonna approximate this by summing, again, weights of the integration points, x, psi integration points, determinant of the Jacobian at that corresponding integration point, where, again, this WIP, psi IP from table. So there's a table for the quadrilaterals, and that table I'll show on Monday after spring break. But it's the same idea. So for any integral, I just need to map to the psi eta space, and then I have some table to know which integration points and what is the weight of each integration point to approximate that integral. All right, I shall see you after spring break. Enjoy, relax. We have a lab on Friday. Relaxed after Friday.